So this file is uploaded, so you can download from Canvas. So this is the given information. So you know for link 2 the mass is given. Okay, center of gravity is given. I2 is the mass moment of inertia. So mass moment of inertia is given. Okay. So for link 3, so you have all the geometric information. Then I3 mass moment of inertia is given. So similarly for link 5 and link 6, so for the slider, because slider is not rotating, so it doesn't have any. Okay, there is no moment of rotational inertia, but it has only the mass. Okay, so all this information is in addition to whatever is given to you. So then you are doing the force analysis for your assignment question. So similarly the force analysis, so you start with your link to the free body diagram. So the link to free body diagram you need to show clearly, then derive. Okay, the procedure is the same. The two equations, sum of the forces acting on the link will be mass times acceleration. Then sum of the torques acting on the link will be I into alpha. Okay, Ig into alpha. So the same two equations we do. See, everything is written. Sum of the forces, sum of the torques. Then you write the x component. Okay, so you write the y component. Then again you write the torque. So this is for link to. It does not happen. Okay, so then you can expand what is R1 to X, R3 to X. Okay, then now for link 3. So link 3 also do the free body diagram. So these equations are the same for all. Okay, so only the parameters will be changing, right? Because your angles are different, your velocities are different, your accelerations are different. So for link 3 analysis, so you can write now the torque is a very lengthy one. So similarly, you can write for your link 4. Okay. So link 5, again you can do the link 5. So link 6 is the slider, so it is simple. So now combining all the 6 links, so your final matrix is like this. Everything is given to you. You are not doing anything, everything is given to you, but you are only calculating these things. Okay? So, and okay, so you are going to find out these things.
Alpha is the arrow, is it? Or is dash?
Second?
The alpha.
Angular acceleration.
The top one is arrow or dash?
This is your unknown quantities. Okay, so this is actually the final equation given. Okay, these are all unknown quantities you need to find out. Okay, so because it is a 13 by 13 or 14 by 14 matrix, so you can't solve it. So you have to use any of the software which you know. You can use MATLAB, you can use Minitab, you can use even engineering equation solver. Okay, any software that can solve matrix inversion. You are going to just input these values. So all the masses are there, so you can calculate this matrix also. So this matrix is known, this matrix is known, so you are estimating the final matrix.
So, do you have to draw the diagrams in the slides?
Free body diagrams.
Yeah, you have to draw the
Yeah. Without that, you can't, there is no basis how you can derive these equations, how you can explain these equations. And the drawing these things, everybody will be the same drawings. And these drawings are also available on Canvas, and I have also uploaded this file. So what is the difficulty?
Screenshot. I just screenshot.
Do we need to write the?
You can't just cut and paste. That feels very again. Now all these things, if you want to draw on your case 1 hour, 1 hour time you need to spend. And this will be a practice for your future project works and other things. So the experience gain will never be go, so it will pay you sometime in the future. Maybe in your job or somewhere else. So you will definitely get value for the money which you have spent. But if you just cut and paste, that actually gives, because I will be knowing it that you cut and paste it. And definitely a student who doesn't do that and prepare his own, so he will be looked favorably. He may be getting 1 mark more. So originality always pays. Alright, is that clear? So you need to calculate this, so you finally will be getting some values for all those things. These set of values, don't worry whether they coincide later with your working model simulation or not, but just list out those values. It doesn't really matter whether you were, whether your values coincide or not, it's immaterial. You may lose half mark or 1 mark, but if you don't do it, you will not get any marks. Okay. So generally, first, you can see the calculated value in this case is quite close, but some of you may not get very close. Okay. So the calculated values may be from your working model. Okay. So then this is from your MATLAB inversion. Okay, from the equations. So there is no calculations involved here because you can't solve the matrix. So everything will be done based on MATLAB inversion. These values which you get from software based on your matrix inversion, these values are you are getting from your working model simulation. Okay, so only for few students, if you do accurately, these two will be very same. Otherwise, I don't expect for 50% you may not get the same values. But don't get this hard time, you just reproduce the same thing. Is that clear? It will be excellent if you get both values straight away, you will get 2 marks. But you can't manipulate the values again. So you have to produce exactly whatever the values you get. Because it has to be shown on working model simulation. Alright, so this is about your second part of your second assignment. Okay, the third part is simply working model simulation. So there is nothing for me to explain on working model simulation. How you can build the model, working model, is explained in the assignment resource file which is available online. So the file is available on Canvas. It will tell you step by step how you can do the model on working WF working model. How you can build the model. Please tell me, let me tell you, it's quite simple. Okay, so then try to simulate and try to get all the values, then compare with your graphical position analysis and graphical velocity analysis, then acceleration analysis. Because from working model simulation, you can get all values including the forces. Okay, so the third part of the assignment is totally working model simulation. So I want to see your report First working model, okay, fully set up with all the meters, okay, no values in it. So then you show for 60 degrees, whatever the angle given to you, right? Theta 2, link 2 is 60 degrees. Fill up your meters with the values. Then tabulate those values and compare with your graphical and analytical calculations. Okay, so working model simulation you must show in your report whether you successfully get or not immaterial. Just record in the assignment. If you don't record, you just don't get the marks. If you record and your assignment is wrong, you still get a minimum of 50%. Is that clear? So if you don't answer part 3, which is working model simulation, okay, you will not get marks. But if you show, get full calculation, then you get full marks. You do, you fail, you don't get good values, you still get good marks. Okay, so your attempt is necessary. I think earlier you have not done working model simulation, right? So because now in engineering dynamics the students are doing working model simulation. So you're supposed to learn the simulations from engineering dynamics. So there are many software available, not only working model, you can also do CATIA, you can also do using this SolidWorks. It's up to you, whichever software you want to use. Working model is the simplest one. There is one more, interactive physics. So there are many software tools where the slider crank can be simulated. Alright, so that is about your assignment part 3. So part 4 I'll discuss next session.
So part 3 is
Part 3 is purely working model simulation.
so this is part 3. This is part 2.
Part 2. Alright, so next we talk about balancing of mechanisms. I think, have you done any experiment on balancing? You have been to on campus? Not yet? Not yet, okay. So we will be doing this experiment. So consider here a link in rotation. So you can come this side, easy for me. Okay, so you can see a simple link in rotation with respect to a fixed axis here. Okay, this is your global coordinate system, x and y. Now, the link 1 has a mass m1, the link 2 has a mass m2. Now, these dotted things will show the centroids. So, the link 1 mass center, link 2 mass center. Now, for the entire system, the mass center is shown here. So, with reference to the global coordinates, the fixed axis, now you can see the combined mass center of the system is not coinciding with the axis of rotation. So here the mass center is away. So this is global mass center is unbalanced. So when this link rotates, okay, so because the mass center is not aligned with the axis of rotation, so it causes a lot of vibrations. Okay, so this becomes an unbalanced link. Now, if you want to balance this link, so the mass center, you need to have a counterbalancing weight, okay, a counterbalancing mass or weight, so that you bring the centroid from here to the axis of rotation. So you make it now by creating some counterweight or counterbalance mass. Make sure that now the combined mass center of the system aligns with the global coordinate axis or with the axis of rotation. So if you do that, then the system is balanced. So this is a balancing only statically. So dynamic balancing means here you are making the sum of the forces acting on the system is 0. So sum of the forces acting on the system for all the links you are making it to 0 by creating a counterbalance mass. So now this is your original link. Okay, so now you are having a balancing mass at a distance, balancing distance, so that the total force acting on the system is now you are making it to 0. Okay, how we can do this static balancing is just calculate the forces acting on each link, make sure sum of the forces will be 0. Okay, so how you do sum of the forces here? Now what is the force acting on link 1? Okay, so force is mass into acceleration, right? So here acceleration is acceleration due to the normal acceleration. Okay, so normal acceleration is r into omega square. So we can write v squared by r. You can also write r into omega square. So you know about this, right? So normal acceleration is v square over r. You can write v is r omega, so r squared omega squared over r. Therefore, you can also write this as r into omega squared. Okay, so if you multiply with mass, you get force. Now the first one, m1 r1 omega square is the force acting on link 1. Now force acting on link 2 is m2 r2 omega square. So now you are creating a balancing mass. So the force acting due to a balancing mass created, the mass of the balance is mb, the position is rb. So mb rb omega square is the balancing mass force. So the sum of these forces must be 0. So all these forces are negative and you are making it to 0. So once you do that, our aim is to calculate the mb rb. Okay, so mb is your balancing mass which you are creating, rb is the distance. Now consider theta 1 is the angle of link 1, so theta 2 is your angle of link 2, then theta b is the orientation or angle of the balancing mass. Okay, so we can write now this mb rb because omega is common. When a link is in rotation with angular velocity omega, all the points on the link will have the same angular velocity. So omega is common for all the links. Okay, so from the previous equation, so you can see omega square you can take out. So you can take out omega square from here, and we can write this equation as mb rb is equal to negative of m1 r1 minus m2 r2. Then you can write, now this is a vector equation. r1, r2, rb, these are all position vectors. So you can write the x component of this vector, then the y component of this vector. So these two are the scalar equations. Okay, so the top one is the vector equation, these two are the scalar equations. Now from these two, you can write now the position vector rb. rb is the unknown, this position, this length. Okay, you can write as rbx square plus rby square under root. Then the orientation theta b, so this is the angle. So you can write tan inverse of the y component of mb rb y over x component mb rb x. So you can calculate theta b and also you can calculate mb rb. So these are the balancing mass. At what angle you need to put, you can get from this. Okay, what should be the radius of the balancing mass, you can get from here. Okay, so either you can calculate mass or you can calculate the product of mass and the position RB. So it is possible to calculate MBRB. So the design factor is, if you decide the mass, then RB will be your unknown. If you know where you want to put the balancing mass, then the amount of mass MB will be unknown. Okay, so basically in static balancing, what we are going to do, we are making sure that the sum of forces acting on the system will be 0. So when you do that, these two are the resulting equations. Okay, so from these two equations, you can calculate the remaining things. Okay, this is static balancing. So now let us do this example. You may just note down this. So now try to understand what is the information given and what is that we need to calculate. So you can see that M1, M2, M3, M4 are given. Okay, so M1 is 200, M2 is 300, this is M4 is 240, I'm sorry, M4 is 260. The corresponding radii of rotation are given, so that means R1 is 0.2, R2 is 0.15, R3 0.25, and R4 is 0.3. So the angles is given, theta 2 is given 45 degrees, okay, then theta 3, 75, theta 4, 130. So the orientations are shown here, the angles. Now what you need to find, the position and magnitude of the balancing mass required. Now the radius of the balancing mass is given 0.2 meters. So you need to find out what should be the balancing mass M at a radius of 0.2 meters, so that the entire system is statically balanced. Okay, so in the exam, normally you will be asked one question related to balancing, and that will be the simplest question. Okay, and normally in the exam you will be asked for dynamic balancing. So that is a bit more, because in dynamic balancing, not only the forces, but you have to make the sum of moments also to 0. Okay, so this is only a simple static balancing. So in this case, you have to make the sum of the forces acting on the system 0. So how we do this? So we just write down the data given. Okay, so we know M1, M2, M3, M4, R1, R2, R3, R4. So this is the balancing mass position given as 0.2 meters. Okay, RC is given as 0.2 meters. Then from the given figure, okay, from the given figure here, so this M1 is along x-axis. Okay, so that means the orientation of this theta 1 is 0 degrees. So then, you know, theta 1 is 0, theta 2 45, then theta 3, you can see it is 130 degrees, then theta 4 is 255 degrees. Okay, so you know all this data from the given description and from the given sketch. Then you calculate what is M1, R1, M2, R2, M3, R3, M4, R4. Okay. So now M1, R1, the magnitude, you know, so you need to find out its X component and Y component. So what is the orientation of this? 0 degrees, right? So this is 40 into cos 0. x component. So this is something like m1 r1 x. Okay. So its y component is 0 because it has sin 0 is 0, right? So it is having only x component. Then m2 r2 x component. So the orientation is 45 degrees here. So m2 r2 into cos 45. Okay. So the x component for this one will be m3 r3 into cos 120. So for this m4 r4 78 into cos, the angle is 255. Then the balancing mass or the contracting mass is mcrc cos theta c. We don't know mcrc, but we know rc. rc is given 0.2. Okay, theta c we need to calculate. So mc and theta c are the two unknowns. So the first one is the x component. So the second one is the y component. Okay. So for the m1 r1 sin theta, sin 0 degree. Then m2 r2 sin 45 degrees. So this one. Then m3 r3 60 into sin theta 3. Theta 3 is 120. So the next one is m4 r4 into sin. Then mcrc into sin theta c. So we write these two equations, x component of all the forces, y component of all the forces here. Okay. Now from these two equations, then you can solve for mcrc. So mcrc is simply mb into rbx square plus rby square. So mcrc you can write down the whole thing, then rc we know. Okay, so from this you can find out the contracting mass required is 116 kg for balancing the system. Okay, then the orientation of this you can take y component of mr sin theta over x component. So that gives you the orientation is 21 degrees 28 minutes. Okay, so the angle, as you can see from the previous one here, so this is theta c. So this is your counterbalancing mass. So this angle should be now 180 plus this. So the total angle is 201.28 degrees. So the contracting mass you are calculating, the distance is given 0.2 meters, right? So that mass we calculated as 116. Okay, so this is for simple static balancing. So sum of the mass forces acting on the system must be 0. So basically we are writing the x component and y component. So the y component over x component gives you the tan theta. So from there theta you can calculate. So theta is tan inverse of y component over x component. So the sum of all the forces. So the first one here is the x component. The second one is the y component. Okay. So it is a simple arithmetic calculations. So normally for dynamic balancing, so first we do the sum of moments to 0, then we will do sum of the forces to 0. But when you are doing static balancing, you are only doing the forces. Okay. Now the same thing you can also do by graphical method. Okay, so try to do the graphical method now. You can do the graphical method. I'll tell you how you can do. So you may just look at the data here. M1R1, sorry. So you know the magnitude of M1R1 is 40 degree, 40 units, right? The orientation is 0 degrees. Okay. So now choose an appropriate XY coordinate axis. Okay. So choose an horizon. Draw 40 units horizontal, 0 degrees. So choose a scale factor, then draw this M1R1 at 0 degrees. Now later actually you feel that drawing the polygon is much simpler doing the calculations. Okay, so this file I have uploaded so you can download later if you want.
So the scales.
You can, it's up to you. Whichever scale you want to do. 1:10 you can take.
还是叫我们画一个
1:5. You can see the
画那
maximum
个
numbers
polygon
are 78.
scale。就是在先画0 degree 因为抵达那跟40 degree 是 M1R1。Yeah, just look 这个轴，所以 I think 是抵达45 degree，所以你画一个45 degree，then 画一个45这样。I think 是这样。
No, omega is common for all the forces, so we are just avoiding omega. So you just write now draw M1R1 40 units along 0 degree. Okay, so that is from here to here, A to B. So the first vector is 40 units, 0 degrees. Okay, so you have drawn the force now acting along mass M1. Now M2 is now at an angle 45 degrees. You can see the angle is 45 degrees. Okay, now no, I'm just checking. So the angle for M2, so the force you have drawn now, right? Now you need to add up all the forces. Okay, so from the tip of, now this 40 units you have drawn, right? Now from here at 45 degrees, you draw the force acting on M2. So you can see the magnitude of the force M2R2 is 45. The angle is 45 degrees. So now from the tip of this force, okay, you are drawing at 45 degrees a magnitude of 45. So you can see here M2R2, the magnitude is 45. The orientation of this is 45 degrees. So this is F1. Okay. F1R1. F1 is M1R1 omega square. Okay. So plus F2R2. So this is 40 units for you. Okay. So if you choose a coordinate axis. So this is your x-axis. This is your negative x. So this is your y-axis negative. This is your y positive. Okay. So what I have done? So the force acting along M1, which is with a magnitude of 40 units and horizontal, 0 degrees. because M1 is horizontal. Now, from here at 45 degrees, I'm adding force 2. Okay, so then from the tip of force 2, I am going to draw the magnitude of 60 units at an angle 120 degrees. So you can choose now at 120 degrees from here. Okay, so what is the magnitude? 60 units. So you draw. So this is F3. So omega is common, therefore we have not used in the calculation. So this angle is 120 degrees. Then M4 R4 is 255 degrees. So from the tip of here, okay. So 245 maybe some I draw. This is 180 plus 60. Now it is 255. So 180 plus 75. So it will be something like this. So this is your F plus. So the magnitude will be 78. Okay, so now you have to complete the polygon. So complete the polygon means, so now we just draw this two. So I can show you the exact one here. So you just measure this distance and you also know the orientation theta. Everything to do is scale. You can use either way. That's why normally you don't use the graph paper, but you take 1 centimeter is the centimeter. So the scale because if you draw to the scale only, then you will get the correct figure. Otherwise, you will not get the correct figure. So could you get the same number, 115 MC?
1, 2, 3.
Then the angle you can measure now from here to here. You can choose the local coordinate axis. Okay, so this angle gives you theta c. practice force muscle. And the measure angle as I shown you that. So now measure this angle from choose your local coordinate axis. I shown you right here. So this is x, y. Okay. Measure from here. Yeah. Correct. How again?
1.5.
Now what is your scale factor?
One is
So measure this. Now 40 units is how much?
my skill is I draw from here.
This one?
4.5.
This is 4. This is 4.5. This is 6 point.
I draw one.
No, your M you get only 23.
Yeah. This right.
Yeah. So that is MC.
Oh, then we calculate. Divided by 0.2.
0.2. Because what
你
you
的
calculate
是
is
这里
Okay.
RC is 0.2.
45，
So this
45
one is equal to over 0.2 gives you
嗯，对，这个 angle 过去应该是
given that
Question.
120呀120。
So you can only measure this length as 23. It all depends on your scale factor. 2.3 or whatever.
What if you don't get exactly equal to?
So generally, if you draw the error of 5% will be tolerated. But let us say instead of 23, you got 22 or 25 or 26, then you're okay. But not 30 or 35. So drawing errors will be tolerated, but not miscalculation or misorientations. Is that okay?
Yeah.
So this one, if you just calculate M into R, you can just plot this polygon, easy. No need for any calculation. Anyone not tapped to your attendance? All of you tapped, right? I need to confirm your attendance. doubt or anything you have? Any questions?
Training is always up here.
No, that is just a drawing error. If you probably use a bigger scale, then your error will be reduced. So what you are doing is you are calculating all the forces, then you are just doing the contracting force here. So making the sum of the forces 0 because the polygon is closed. The force polygon is closed. Shall I move on to the next question?
So we need to mention the F2 equal to M to R square.
No, that is for your understanding and review.
So I draw the
No need to show. Alright, so let's take this question now. So here there is a circular disc attached 3 masses, 4 kg, 3 kg, 2.5 kg, and they are positioned at 75 mm, 85 mm, 50 mm, and at the angular positions of 45 degrees, that is theta 1, theta 2, theta 3. The angular positions are measured counterclockwise, means okay, the direction is positive. So from the reference line along the x-axis. So determine the amount of the contour mass at a radial distance. So here RC is given, which is 75 mm. Okay, for static balancing. So you need to calculate the contour mass. MC you need to calculate. And of course you also need to know the orientation of this balancing mass. So M1, M2, M3 given, we write down. R1, R2 write down. Theta 1, theta 2, theta 3. Then just calculate what is M1, R1, M2, R2, M3, R3. Okay, so now you can plot this. So try to plot. So M1, R1 is the magnitude is 300, the orientation is 45 degrees. So you can just choose a coordinate axis. So we draw 300 units at an angle 45 degrees. So let us say this is your 300. Then from the tip of that vector, you draw at 135 degrees, 255. So choose a local coordinate axis here. So at 135 degrees, you are going to draw. So something like this. So this is 255. Then from here at 240 degrees, so you are drawing at 240 degrees, the magnitude is 125. So this is 125. Then you complete the polygon. So this is 340 degrees. So the figure should something like this. So your final diagram will look something like this, and you may check your values. So the measurement will give you about 285 or 286. From here. No calculation. So when you know this M1 alpha is 300, right? At an average of 10. Okay. So choose a scale. Let us say you take 1:100. Okay. So your M1 alpha will be only 3 units. Then plot the scale. 1:100. So the second one will be 2.5. Because 255 and if not, we will be plotting only for 2.5. So similarly, M3 I'm plotting only 1.25. So you can see this is 300. Whatever the scale it may be. Okay. Now this length represents 255. But at an angle you need to plot based on the orientation scale. Okay, so then this length is only 185. So this is force 1 plus force 2 plus force 3. Then force 4. So the sum should be 0. So that means you must close the polygon. So whatever is now you measure this distance. So that will give you MC RC. So that is this much. Okay, then you divide this with the RC value is given, then your 75 RC, so MC will be 3.8. Yeah, you can guys, any questions or any doubts? Second? Correct. Countermass distance means quite sharp countermass. Then you can measure the direction of that, the orientation of that. So you can see how to measure it. So now imagine a local coordinate axis here. Measure this angle. Come out that. So that will be about 8 to 7. Is that okay? So if you're okay, I'll go back to the next question. Okay, let me know when you're ready. How I get? 285 is the length from C to O. Alright, can I move on to the next one? Okay, so the next part is now static balancing means you are only summing the total forces acting on the mechanism to 0. So you are balancing the force only. So now in two plane, okay, when the system is moving in a plane, then not only the forces but also the movements need to be balanced. So that means you need to make sure that some of the movements acting on the system will be zero. Okay? So when some of the movements acting on the system means, now if you have a system like this, okay? So for example, there is a mass M1 here, mass M2 here. Okay? So consider with reference to a point, so M1 is located at a distance L1 and M2 is located at a distance L2. Okay? So there will be a movement acting on this system. So for dynamic balancing, we need to make sure the sum of movements acting on the system will be zero. Now you just focus on the figure given here. So look at the figure given, so you will get the concept of the dynamic balancing. Now M1, M2, M3 are the three masses. Okay, M1 is located at L1 from a reference point or from a correction plane. Okay, and M2 is located L2 horizontally, M3 is L3. Okay, so now we need to create balancing masses, or we also call correction planes here. So we call a correction plane MA and MB. Okay, so now the distances measured with reference to the correction plane L1, L2, L3, and the correction distance for the plane B is LB. Okay, so now what are the forces acting on masses? So in actually the orientation, the masses are located like this. So the force acting on mass 2, okay, is M2 R2 omega square. Force acting M1 is M1 R1 omega square. So these are the forces on the three masses. Now we have the two correction planes now, okay, A and B. So the force on A is MA RA omega square. The force on correction plane B is MB RB omega square. So we know the orientations also. Theta 1, theta 2, theta 3 will be given to you. Now we need to know the orientation of theta A and theta B. Okay, so in this case, what we need to do is not only the sum of the forces, but we need to do sum of the movements acting on the system to be zero. What is movement? So force multiplied by the perpendicular force. Right now we know the force acting here. Now we know the perpendicular distance. So we can first write some of the forces acting on this. Okay, the first one we write the total force acting on the system is zero. Okay, M1 R1 omega square is the force acting on mass 1. So similarly M2 R2 omega square is the force on mass 2. So we sum all the forces to zero, then omega square is a common factor, so we just take out the omega square. Now you can rearrange these terms as MA-RA plus MB-RB is negative of M1 R1, M2 R2, M3 R3. So now this is a vector equation. Now this equation we are writing into two scalar components, x and y. Okay, so this is just like the previous one. So we are just equating the forces to zero. Okay, so now you have these two components. Now we are now writing the moments acting on the system. Okay, now with reference to point A, so we are summing the moments with respect to the correction plane A. Okay, so the total moments with respect to correction plane A is zero. So that means the force M1 R1 omega square into L1 plus M2 R2 omega square into L2 plus M3 R3 omega square into L3 plus M3 MB RB omega square into LB should be zero. So that is what is written here. So with reference to correction plane A, the moments are zero. So that means the movement MB RB omega square into LB should equal to the sum of the moments acting on the remaining three masses. So you can write M1 R1 omega square into L1 minus M2 R2 omega square into L2 like this. Now from this again, this is a vector equation, so you can see omega square is common, so you can take out omega square from this equation. Now the R1, R2, R3, RB, these are the vectors, the position vectors. So you can write in terms of the components. So the first one you write x component, and the second one you write the y component. Okay, so now you know everything here. So that means you can calculate what is MB RBX and MB RBY. So that means basically once you know these two things, okay, you can calculate the x component, y component, then you can calculate the magnitude, then you can calculate the orientation. Once you know MB RBX, MB RBY, then you can go back to this formula. Okay, so you know MB RBX, MB RBY, then you know all these things. So therefore, you can also calculate MA RAX and MA RAY. So that means you can calculate the correction plane masses MA and MB, and also the distances RA and RB. So for dynamic balancing, we need to do first the movements to 0, then we need to do the forces to 0. Okay, so you can understand this by doing the calculations you can see here. So this example says a shaft carries 4 masses A, B, C and D. The magnitude of the masses are given. So 200, 300, 400 and 200. And revolving at a radii of, so this is R1, R2, R3, R4 given. Okay, in planes measured from A, so the plane, correction plane is A, so the horizontal distance measured from A. So L1 is 300 mm, L2 is 400 mm, L3 is 700 mm. So the angles are given. So this is theta 1, theta 2, theta 3. Okay. So the balancing masses are to be placed in planes X and Y. Now the distance between the planes A and X is 400 meters. Okay, all the geometric information is given. So you can visualize the figure as shown here. Okay, so you can see the position in planes. Okay, the 3 masses are A, B, 4 masses A, B, C, D. Okay, so the X and Y are the correction planes. Okay, now the distance from the correction plane X to A is given as 100. Okay, then the distance from correction plane Y to D is given 200. Okay, all the distances are given here. So from plane A to B is given 300, then plane A to C is given. Okay, mass A to mass C is given distance, then mass A to mass of correction plane Y is given, and also the distance between mass A and mass D. All the distances are given based on the description here. Okay, so based on the description, you will be able to locate the position of the correction planes X and Y and the masses A, B, C, D. Okay, the 4 masses. Okay, in angular positions, you know the orientations are also given in angular positions. So A, B, C, D are the masses. So the dot, the blue circles indicates the correction planes. Okay, this is correction plane X and Y. So the angles, as see, the angle between A and B is 45 degrees. Then the angle between B and C is 70 degrees. Then the angle, okay, as described here. So all the angles are mentioned here. Okay, so now you know the orientation of the masses in angular position and also on planes. So now you list out MA, MD, MC, MD given. RA, RB, RC, RD given. So theta A, theta B, theta C, theta D given. LA, LB, LC, LD, LY is given also, RX and RY given. So what we need to calculate? The counterbalancing masses on the planes X and Y. So this is mass Y, this is mass X. Where you need to put at 100 mm. So the distance is given. Okay. So is that clear? All the given information you are listing out. Okay. Later we write this as M, mass data, position data, orientation data. So this is the horizontal plane data. So M, R, L data. M, mass, R, position, L is the horizontal distance. So to solve this, okay, we can first do the sum of the calculation method. So analytical method, sum of the moments acting on the system will be 0. So that means if you reference to plane X, you can write the moments acting, okay, on plane Y should equal to the whole thing. Okay, MRL cos theta square plus MRL sin theta square sigma. That means for each mass. So there are 4 masses, M1, M2, M3, M4. So calculate M1, R1, L1 into cos theta 1 square plus M2, R2, L2 cos theta 2 square, like that for all the 4 masses. So the data is shown here. So the first one is M1, R1, L1 into cos theta. So for mass M1, theta is 0. So you can refer this. Okay, L1 is 100 mm, RA is 100. So MA into 200 into 80, 160. So it is taken as 1.6 here. So correction factor 1:100. Okay, so the first one all X terms. So the second one all Y terms. So sum of this should be equal to MR LY. Okay, so you can just calculate this, and from there you know LY is known, RY is known, therefore you can calculate MY. So the correction mass on plane Y should be 184 kilograms. But at what angle, again, you can take Y component over X component. Okay, so simply you know tan theta is Y by X, right? So theta is tan inverse of Y over X. So here Y means the Y component of all the forces on the masses. So there are 4 forces, so 4 X components, 4 Y components. Okay, so you can do this. Sum of moments acting on the system will be 0. Okay, so then you know the mass acting on plane Y and also the orientation of the plane Y. So after that, then you can do the sum of the forces acting on the system 0. Okay, so now this is sum of the forces acting on the system. Okay, so you can write analytically the forces acting on the X component and Y component. So this is X component square, Y component square. So you can just calculate, putting all the values there, then calculate mass on the X plane. Then you can also calculate the orientation. Okay, so this is analytical method. So you can see analytical method requires a lot of calculations, right? Next, let us do the graphical method. So graphical method, you may just draw a table like this. Okay, so how many masses are there? A, B, C, D, 4 masses. So what are the reference planes? X and Y. So first, the position between mass A and D is given, okay, from the description. So X is in between A and B. Okay, we just position all the given data. A, X plane, B, C, then Y plane, then D plane. So how we can arrange this based on the description of the problem. Okay, then the orientations of the planes given, the masses are given, the radius given for all the planes. Okay, wherever we do not know, so for example plane X we don't know the angle, so we write theta X. So for mass of plane X we don't know, so we write mx. Similarly for Y, we don't know the angle for plane Y and also the mass Y. Okay, the radius for all the planes are given, so similarly you calculate the mr, mass into radius. So for example for plane 1, for A, mass A, so what is this? M is 200, R is 0.08, M into R is 160. Okay, so similarly for B, M into R is 300 into 7, 0.07, so it is 21. So for plane X, we know radius, but we don't know the mass, so we just write 0.1 into mx. Okay, so like that you fill up the column M into R. Now the distance from reference planes are also given. Okay, so we follow the notation with reference to the plane towards left is negative, towards right will be positive. So mass A is negative 0.1 from X plane. So we are referring the data to plane X, so therefore the distances of for plane X reference point will be 0, 0. Okay, so the last column is M into R into L. Okay, so M, R, L. Otherwise we have MR column, so multiply with L column. So you write M, R, L column. Okay, so you need to prepare the table first. Okay, then first we are drawing MRL polygon. So MRL polygon means what is the data? You can see the last column. Okay, so focus on the last column. So for dynamic balancing, we need to plot two polygons. The first one is called as MRL polygon. So we write mass into radius into L. Okay. Okay, first see for the plane A, MRL value is negative 1.6. Okay, and we know the orientation of this MRL. So that data you can see from the previous one. So the orientation, okay, so the angle is given 0 degrees. Okay. So choose a coordinate axis. So MRL value is negative 1.6. So just draw negative 1.6. 0 degrees. Now from the tip of that plane B, the value is 4.2. Okay, and the orientation is 45 degrees. Okay, so from the tip of this at 45 degrees, so you're plotting a magnitude of 4.2. So this is the MRL for A plus this. Okay, then from the tip of that you are plotting for mass C 7.2 units. Okay, MRL is 7.2. Orientation is 115 degrees. Okay, so from the tip of this, now choose 115 degrees. So 115 degrees may be something like this. The magnitude is 7.2. So just draw 7.2. So this is 115 degrees. Okay, MRL value. So then look for D. So the value for D is 9.6 and the orientation is 235 degrees, right? So then we are plotting this 9.6, the orientation is 235. So from the tip of here, okay, we are going to plot at 235 degrees. So imagine this is local coordinate axis, 180, 235 is something like this. Okay, so the magnitude is 9.6, so you can draw a bit longer. So this is 9.6. So you can see here, okay, this is negative 1.6 drawn at 0 degree. Then from the tip of that you are drawing 4.2 at 45 degrees. Okay. Then from the tip of this you are drawing 7.2 at 115. So this one. Then 9.6, okay, and drawn at 235. So you came to D dash. So now we complete the polygon. So this gives you whatever the distance you measure, the dotted line. So that is equivalent to this value, 0.04 into M1. So because you are summing all these things to 0. So you're summing all the values, MRL values to 0 because you're closing the polygon. So the sum of all the things will be 0. So focus on this. So now you can, all the blue lines indicates the data which you have plotted. Okay, so then the dotted line in pink shows you the balanced. So that is equal to this 0.04 into My. So that is the values for the correction plane. Now you measure from your sketch how much you get. Okay, so it is measured as 73 kilogram meter square. Now over 0.05 that gives you the balancing mass on plane Y is 182.5 kilograms. So when you are doing dynamic balancing, always we draw the MRL polygon first. So we are making some of the movements to 0 first. So once you do this, now you know this column. My is done. Okay, so you know My. Now only Mx you need to find out. Okay, so once you know My, now you plot MR polygon. Okay, so 0.1 into My you already know. Now 18.2. Okay, so now we are plotting the MR polygon. So MR polygon. So we know this value now 0.1 into My because My is 182.5. Okay, so next we try to plot MR polygon. So MR polygon means we need to focus on the values here. Okay, so 160 0 degrees. Okay, so we are just drawing 160 lines. So the scale factor is taken 1:10. So instead of 160, it is shown 16.
I think the 160 is wrong because 200 times 0.08 is 16.
M into R.
Yeah. I
Oh.
mean, yeah. You see the last column also 200 times 0.08 is 16. So by right, I think that one should not be 160. It should be 16.
With calculation, yeah. The first one should be 200 into 0.08 is not 160 but 16 only. Okay, so it should be only 16 typo here. So we just plot horizontally 0 degrees, 16 units. Then from the tip of that at 45 degrees, okay, so you know MR value, so that is 21. So from the tip of that you are plotting 21, okay, at 45 degrees. Then from here you are plotting 24 at an angle 115. So this one is at an angle 115. Then from the tip of C you are drawing 16 units. So where is 16? So this one. So at an angle 235. Okay. So now you are plotting this 0.1 into my. So you know my value already. So how much my is? So you are plotting 0.1 into 182.5, so 18.2 something. So that value you're plotting here. So after that, so now all the blue lines are done. So now try to complete the polygon. Okay. So whatever the dotted line now indicates, okay. So the value will be 0.1 into mx. Okay. So you can measure from your drawing. So then divide by 0.1. So that gives you the mass of the x plane. And also you can measure the orientation of the plane. Okay, so you can also measure the direction of the plane from the point where you close the polygon. Guys, is that clear? Any questions or anything not clear? And let me tell you, this type of question will be asked, dynamic balancing, and that should be the simplest question. So both dynamics and force question will be rather simple. So dynamic balancing, you can do calculations or you can also use graphical method. But always graphical method is simpler. Let me know anything which is not clear. You can try to do this question first. Okay, this is a rather simple question you can do.
Previous one. The MY, how did we get it?
Which one?
The
My you calculate from the MRL polygon. You will see this polygon first. Okay, that's what I have done here. Okay, so once you do this, you stop here, right? So you just complete this. Now you measure whatever is the distance from your drawing, multiply the scale factor, that gives you 0.04 into y. So as you can see the dotted line here. So the value of this is 0.04 into my. So 0.05 my measured is 73. So from there my will be just divide by 0.04. So divide 73 over 0.04. So that gives you 182.1. So that means now you know here my value. So that means you know this value MR value. So next you are plotting MR polygon. Is that okay? Okay. So you do the next this one example. But this one is simple. Static balancing. So it is static balancing only. So you are only plotting MR polygon. So write down the values, M values, R values, then write down MR values. given, so we write balancing mass MB. The distance is given 60. Okay. So this will be MR will be 60 times MB. So this will be theta B. So you can plot now MR. So I draw 130. Then 50 at 30 degrees. Then 56 at 130 degrees. Then we can complete this. So the value will be 60 times MB. So this one measure how much? So anyone got the answer? What's your name? 2.9. About 2.4. So the is measured as 143. So the answer is about 2.4 kg. The direction is 208 degrees. This current angle is 130 degrees, right? R from this point 100 degrees. How much angle? What is that? 20 degrees measured from this. So otherwise 150 degrees. So I wrote as 130 so that you can follow the original way. Because this is not 130. 130 is what? Around 2.4.
Yeah, 2.4.
Yeah, you get very close.
Same. So 这样。你拿多少？172，我拿144。
Because if you see the figure here, this is 30 and this is 100. Correct. Correct. Then the angle between B and C is 100 degrees. So when you measure from point A, it will be 150. If you want to make it 100, you need to measure with respect to this. Measure this, you make it 100.
嗯。
So, okay, then we do one more question where you have to do both MRL polygon. So try this one. Okay, this is also static. Now we try this one.
这个是130，那个 angle 130，因为它是30
So
嘛，
find the mass
对，它
and
30
angle
加
at
100。
which it should be positioned in planes A and D at a radius of 60 mm in order to produce complete balance of the system. So this is where you need to do both static and dynamic balancing, both. Some of the forces need to be zero and also the movements need to be zero. So mass B is given, mass C is given, RA is given, radius B is given, radius C is given, then the orientation of the mass is given. So you can prepare similar table. When you are doing here, you will have L also. So you can fill up MRL column. Okay, so 375 into 200 you can write down, 100 into 300 you can write down. Okay, so here will be 660 times 375. Because we need to find out mass A and mass D. Okay, the angle between B and C is given 60 degrees. So now you can see mass A, 5, 2, mass D. Then you can write 60, 75, 50, 60. Then M into R, so you can write 60 times MA. 375, that is 5 into 75. This is 50 into 2, then this is 16. So the L is first one 0, 200, 300, 375. So then prepare this R into L. So this column you can calculate. So 375 into 200 is 75,000. So you can write 75,000 here. So here is 30,000. So here will be 22,100. Okay, okay, so first I'm going to plot MRL polygon. Okay, so the first one is 0. So now we know the mass C is, so you can see the angle between B and C is 60 degrees. Okay, so so B is, you can see the angle B is vertical along y-axis. Okay, so you can plot now 75,000. So you choose coordinate axis. Okay, so B is along vertical axis. So plot this 75,000 along y-axis. Okay, and C is at 60 degrees from B. Okay, so you can plot, this is 30,000. So then you need to just complete here, there are only two things. So this will be your completed polygon. So try to measure that. So this is the polygon I am referring. So this one. So B is vertical. So the magnitude is, the MRL magnitude is 75,000. So choose an appropriate scale. Okay. So choose an appropriate scale and draw this 75,000. Now from the tip of that you can draw this 30,000 at 60 degrees. So you can draw this vector. Okay, so B and C, the two. Then we know MRL for plane A is 0 because we are referring the movements to plane A. So the movements are 0 for plane A. So then just complete this two. So that gives you, for plane D, what is MRL is 22,500 MD. So whatever this distance you measured is equivalent to 22,500 MD. So from this mass of D you can calculate by just dividing. So the measured distance is 94,000 from this figure. So we need to confirm that value.
So from B to C, how do you draw the local axis?
From B is vertical, right? 75,000. So from here, put 60 degrees. If you see, the angle between B and C is 60 degrees. So B to C is 60. So with respect to this, I think this angle is 60 with respect to vertical, not horizontal. So from B to C, right? So the angle is 60. So B to C. So with respect to horizontal,
But even with respect to the vertical, actually going down to the horizontal.
no, we are just adding the vectors here.
Right.
So the force along B plus the force along C. We are just adding these two. So ultimately we need to make sure the total forces to be zero. So that means we need to, total movement, sorry, here, because we are drawing MRL first, right? So we are drawing MRL. So total movements with reference to A, you are making it to zero. Okay, so that means whatever the measurement you do here, that gives you 22,500 MD.
Actually, what I mean was that based on the diagonal and find out
No, you plot at C.
because I thought that based on this, the local axis of the I thought this the 60 should be coming from here instead of here. Right now, based on the figure only, right, 50 degrees come from here, right? Shouldn't it be over here instead?
No, no. It is because with reference to the vertical, you can see the orientation from here. So B to C is 60. So if you take a horizontal with respect to horizontal, the angle will be 30. Alright, so from MRL polygon or MRX polygon as shown here, so you can only measure this distance and multiply with your scale. So that gives you 22,500 into MD. So from this you can calculate mass of D. So as shown here, the mass of D is 4.17 kilograms, and the direction of this is 254 degrees. So you can choose a local coordinate axis and measure the orientation here. So you can always see that this is 180 plus something, so this 254 is okay. So once you do this, then your MD value you know. So you know MD value. Okay, so that means this MR polygon, you know, 60 times MD. Okay, so you will be knowing this value. So next you are going to plot MR polygon. Okay, so MR polygon only focus on this. So 60 MA is unknown. So start with 375. So this is 375 MR. Then at 60 degrees from this, okay, with respect to B. Okay, so measure with respect to B 60 degrees. The magnitude is 100 MR magnitude. Then 60 times MD. So MD value we know is 4.17. So 60 multiplied by 4.17, that value is 250.68. So you're plotting at 254 degrees. Now choose a local coordinates and plot this same direction. So it is 254 degrees. Okay. So you plot now the three vectors, then combine these two, join this. So here the length of this vector gives you 195. So 195 is equivalent to 60 times, 60 times MA. So 195 is equal to 60 times MA. So from there you know mass of A is 3.25 kilograms. And the angle of this you can measure, okay, with respect to vertical. So if you choose a vertical here, so here the angle is measured with respect to a vertical, which is 6 degrees. So otherwise you can also give the orientation of this. Okay, so you can also give the orientation with respect to any local coordinate axis. Is that clear, guys? Any question? Which one? No, the entire concept is focuses on preparing first the table. So whatever is the data prepared, okay, mass, radius, okay, horizontal distance L, then write down MR, then MRL. So first you are going to plot MRL polygon. Okay. So when you do, always you refer this to a plane. Okay. So for that plane, MRL value will be 0 because L will be 0 for that plane. So the reference point. So the reference point L is 0, so therefore this is 0. So in this case, we are choosing the plane A as the reference plane. Then you know for mass D, the value is 35,000, mass C, the value is 30,000, and for mass D, we don't know the mass D also, so we write 22,500 MT. So now you just plot these things according to the angle, complete the polygon. So the distance gives you, the dotted distance as you see here is 22,500 MT. So from there you know the mass value. Mass for the plane D, the counterbalancing mass for plane D. So once you know that mass, that means now you know this is known. So we now look for MR polygon. So this value is known. So the only unknown is this MA. Then as per the orientations, now plot MR polygon. So the last to complete the polygon, so you will be drawing the dotted line. So the length of that gives you MR value. So this 60 times M. So the calculations are shown now. So this is about the dynamic balancing. So there could be a number of problems related to dynamic balancing. Okay. The point is, listen carefully. Okay. Follow what Dr. Firoz does in the pre-exam workshop. Don't miss, for God's sake, please don't miss pre-exam workshop. He will take at length in explaining things. Because for me, 6 sessions, we need to discuss theory, we need to discuss assignments, so I'm a bit rushing.